The objective of this lecture is to provide an introduction to tensors. A tensor, also known as a second-rank tensor, or a tensor of rank 2, is a linear operator whose input is a vector and whose output is also a vector. A tensor is denoted by the general notation T with two underbars. So you'll notice there that there are two underbars. And that distinguishes it from a vector, which we generally denote with one underbar. Now, because of the properties of a tensor, so these are the key constructs that arise with tensors, is that a tensor T satisfies the following two properties. The first of these properties is that if you apply the tensor T to a vector B, I could actually call this a vector A, you get a vector B. The second property is that if you apply the tensor to a linear combination of vectors, alpha A plus beta B, you get alpha times the tensor applied to the first vector plus beta times the tensor applied to the second vector. Now, this is actually, the second one is actually linearity. And we can define here where A and B are vectors and lie in three-dimensional Euclidean space, and alpha and beta are scalars. Now you can see that the input to a tensor is a vector and the output is also a vector. So tensors lie in what is known as E3 by 3. So in other words, it's 3 by 3 Euclidean space. That's the space in which tensors lie. Now those are the properties of a tensor. The first one is, again, that the input of a tensor is a vector and the output is a vector. And the second is that a tensor is a linear operator on vectors. So the second condition here is linearity. So now what we can actually do is we can start using this. We can start building constructs of how we actually represent tensors in coordinate systems, and we're going to work our way through these things in the rest of this lecture. In order to be able to start that discussion, we need to actually define a key construct, which is what's called a tensor product between vectors. So a tensor product between vectors is defined as follows. So let A and B be vectors. So that means that A and B are elements of three-dimensional Euclidean space. Then the tensor product between A and B is defined as follows. Actually, before I could say denoted, we'll give the notation. A circle cross B is defined as A circle cross B operated on C is equal to B dotted with C times A, where C is also a vector. And so that means that C also lies in three-dimensional Euclidean space. Now, you can actually see that from this definition, we can actually show that A circle cross B is in fact a tensor itself. So A circle cross B is a tensor. How do we know that it's a tensor? Well, the first thing is, what's the input to A circle cross B? So the input to A circle cross B is a vector, and the output is also a vector, right? So let's write that down. So the first thing is the input to A circle cross B is a vector. In this case, that vector is C. The output of A circle cross B is also a vector. And in this case, that vector is B dotted with C times A. So we know now that the input is a vector and the output's a vector. Now the question is this operation linear? So let's actually look at this. So A circle cross B operated on a linear combination of, say, two vectors, gamma C plus delta D, is going to equal, well, let's do it. So if we do it, we get A circle cross B applied to gamma times C plus, maybe write this a little bit smaller. So A circle cross B applied to gamma C plus A circle cross B applied to delta times D. Now that's equal to gamma times A circle cross B applied to C plus delta times A circle cross B applied to D. So that implies that A circle cross B is linear. So because the input is a vector and the output is a vector of A circle cross B, and A circle cross B is linear, that implies that A circle cross B is a tensor. So now how can we actually express tensors? So this is where we were headed a few minutes ago, and we first did this tensor product. Suppose now that E, which I'll denote with 2 underbars, is equal to E1, E2, E3, is a right-handed orthonormal basis for three-dimensional Euclidean space. Then the vectors A and B can be expressed in the basis E as A is equal to, well, it's the summation from I equals 1 to 3 of AI EI, which is also equal to A1 E1 plus A2 E2 plus A3 E3. And b can be written the same way as the summation from I equals 1 to 3 of bi ei, which is equal to b1 e1 plus b2 e2 plus b3 e3. So now, given that, let's compute the tensor product between a and b. So then, the tensor product between a and b is going to equal the sum from I equals 1 to 3 of ai ei, and then the tensor product with the sum from I equals 1 to 3 of bi ei. Which, if we go through all the tensor products, we wind up with the following. You can see that the vector A expressed in this basis E, and similarly the vector B expressed in this, they're going to be all these tensor products which are going to be formed from EI circle cross EJ. So this is actually going to equal the sum from I equals 1 to 3 of the sum from J equals 1 to 3 of AI BJ EI circle cross EJ. Now, of course, if you want to do this out more explicitly, you can, which for the first time maybe it's worth just doing it just to be able to see that that's the case. So this is equal to A1 E1 plus A2 E2 plus A3 E3, and that tensor product is taken with B1 E1 plus B2 E2 plus B3 E3, and that's equal to, well, let's take all the products now. We get A1, B1, E1, circle cross E1, plus A1, B2, E1, circle cross E2, plus A1, B3, E1, circle cross E3, and then plus A2, B1, E2, circle cross E1, plus A2, B2, E2, circle cross E2, plus A2, B3, E2, circle cross E3, and then finally plus A3, B1, E3, circle cross E1, plus A3, B2, E3, circle cross E2, and then finally plus A3, B3, E3, circle cross E3. And I did all of these, all the cross tensor products between these basis vectors. And this, of course, now gives me back the result that I had written down originally, which I'll repeat just for completeness and perhaps a little bit more clarity. Now you could see that what happens in the process of this is that the tensor product between A and B can be written in terms of these quantities EI circle cross EJ. So the quantities EI circle cross EJ, where I and J go from 1 to 3, are called basis tensors for 3 by 3 Euclidean space. Now, you can see that 3 by 3 Euclidean space implies that there would be 9 quantities that would need to be used in order to be able to represent any instantiation of a tensor, right? So and you can see that there are 9 basis tensors, right? Because EI circle cross EJ, I and J go from 1 to 3, so there are 9 basis tensors. So a tensor can be written in terms of basis tensors. So let's write that. A tensor can be expressed in terms of basis tensors. And there are 9 of them. And there are 9 basis tensors. So now we actually have a way of being able to write a general tensor. So we can say that a general tensor T can be written as the sum from I equals 1 to 3 of the sum from J equals 1 to 3 of Tij Ei circle cross Ej. Where in the case of the tensor product between two vectors A circle cross B, these coefficients Tij are actually equal to Ai multiplied by Bj. But in general, they're just some coefficients Tij, and I and j run from 1 to 3. Now, from this, we can actually start using this construct of a tensor in terms of a basis and in terms of basis tensors to be able to do operations. So the first thing we need to do is in order to do that, is we want to know what happens when we apply a tensor to a vector. Okay, so suppose now that T is a tensor and A is a vector. It is desired to express the operation T applied to A in terms of a basis, which again I'm going to just label this basis E, which is equal to E1, E2, E3. Now the first thing that we need to do is we need to actually define a construct which we will use, and you'll see this construct in just a second. Let's look at this, and you'll see that it'll come out from the operation. So we know that T can be written in terms of this basis as the sum from I equals 1 to 3 of the sum from j equals 1 to 3 of Tij Ei circle cross Ej. That's what I just wrote down a short while ago. Well, the vector A, again, can be written as the sum from I equals 1 to 3 of Ai Ei. So what happens when we take T and we apply it to A? Well, we get the sum from I equals 1 to 3 of the sum from j equals 1 to 3 of Tij Ei circle cross Ej, and then this is operated on the sum from I equals 1 to 3 of Ai Ei. Now, in order to be able to do this operation, you'll see that when we're going to write this whole thing out, so you can actually view it in terms of the individual terms. And this is how we're going to do that. Is that notice that in order to compute T applied to A, it is necessary to compute quantities of the form Ei circle cross Ej applied to Ek. We're going to need to do that. And we'll actually see it very explicitly in just a minute, but let's actually do this first. So, using the definition of the tensor product, which is from earlier, or I could say which from earlier is that A circle cross B applied to C is equal to B dotted with C times A. We have the following. Ei circle cross Ej applied to Ek is equal to Ej dotted with Ek applied to Ei, or multiplied by Ei. Now you can see that that just came straight from the definition of the tensor product. That is then equal to one of two things. Well, this basis, E1, E2, E3, is a right-handed orthonormal basis. So if j is equal to k, then Ej dotted with Ek is going to equal 1, and I'm going to get Ei for the final result. If j is not equal to k, ej dotted with ek is 0, and so this whole thing is going to wind up giving 0 for j not equal to k. Now we can use that fact in this tensor product. So, the tensor product with the vector. So the tensor is being multiplied by the vector. So now let's go back to this expression over here that we have on the previous page, and let's write this whole thing out. We've got T11, E1, circle cross E1, plus T12, E1, circle cross E2, plus T13, E1, circle cross E3, plus T21, E2, circle cross E1, plus T22, E2, circle cross E2, plus T23, E2, circle cross E3, plus T31, E3, circle cross E1, plus T32, E3, circle cross E2, and then plus T33, E3, circle cross E3, and then this whole thing is operated on A1, E1, plus A2, E2, plus A3, E3. Now, let's actually write this out and see what happens when we use the property. We're going to be using this property that I just derived up above of EI circle cross EJ dotted with EK. It's either equal to EI or 0 depending upon whether J is equal to K. Let's look at the first term. I've got T11, E1 circle cross E1, and I'm going to multiply that by A1, E1. Well, E1 circle cross E1 operated on E1, if I follow the rule that I see up at the top here, gives me T11 A1 times E1. And then the next one is going to give me 0. E1 circle cross E1 operated on A2, E2 is 0 because E1 dotted with E2 is 0. And the same thing goes for E1 circle cross E1 operated on A3, E3. Now I go to the next term. I've got T12, E1 circle cross E2. If I operate on A1, E1, I get 0 because E2 dotted with E1 is 0. And again, I'm just following the rule up at the top. And then if I take E1 circle cross E2 and I operate on E2, I get E2 dotted with E2 is equal to 1, and then that's multiplied by E1. So I get plus T12 A2 times E1. And then if I go through the same result on T13 E1 circle cross E3, I get plus T13 A3 multiplied by E1. And then I'm going to do the same thing for the next two rows worth of terms in this expression, and I'm going to wind up getting T21 A1 E2 plus T22 A2 E2 plus T23 A3 E2, and then plus T31 A1 E3 plus T32 A2 E3 plus T33 A3 E3. Now if I write that out further, I get T applied to A is going to equal T11 A1 plus T12 A2 plus T13 A3 multiplied by E1 plus T21 A1 plus T22 A2 plus T23 A3 multiplied by E2, and then plus T31 A1 plus T32 A2 plus T33 A3 multiplied by E3. So now let's look at this and let's see what this actually looks like in terms of things that may be a little bit more familiar. Is that suppose, so we can recall this from earlier. So recall that if we write the matrix, or we write T in this basis, which I called E, it's equal to this matrix T11, T12, T13, T21, T22, T23, and T31, T32, T3, 3. And then similarly, if I express the vector A in terms of the basis, which I called E, I get A1, A2, A3. So as a result, this operation, T applied to A, if I now express that in the basis E, I get the following. I get T11 A1 plus T12 A2 plus T13 A3, T21 A1 plus T22 A2 plus T23 A3, and then T31 A1 plus T32 A2 plus T33 A3. But that is equal to the matrix T11, T12, T13, T21, T22, T23, T31, T32, T33 multiplied by A1, A2, A3, which is equal to the matrix representation of T in the basis E multiplied by the matrix representation of the vector A in the basis defined by E, which is E1, E2, E3. So what this tells me is that multiplying a tensor by a vector, when I finally express that tensor and that vector in a basis, is equivalent to multiplying the matrix representation of the tensor by the column matrix representation of the vector. So let's write this down. So the product of a tensor T with a vector A when the tensor and the vector are expressed in terms of a basis E, which is equal to E1, E2, E3, is equivalent to multiplying the matrix representation of T in the basis E with the matrix representation of the vector A in the basis E. Now, you can actually see that what that says is, it says the following. So those are the words, and then here's what it says in math. It says that T applied to A when expressed in a basis E is equal to the matrix representation of T in the basis E multiplied by the matrix representation of the vector A in the basis E. Now, because of that, we can actually associate matrices with tensors, but it's very important to understand something. This is a very key point, and it's really important to keep this in mind. A tensor, analogous to a vector, is a coordinate-free quantity. It's very important to understand that. It doesn't have anything to do with coordinate systems. The representation of a tensor in a basis, and remember, the basis in this case is actually EI circle cross EJ. It comes from the basis E1, E2, E3, but it's these basis tensors that I'm working with. In a basis EI circle cross EJ, that representation is dependent upon the coordinate system. Which is, in this case, the basis because we're dealing with bases. So what that means is as follows. So as a result, if a new, or I should say an alternate basis, let's call this E prime, which is equal to E1 prime, E2 prime, E3 prime, is chosen, then the tensor T has the form, I should say in the basis E prime has the form, or has the representation, perhaps I should say that. T expressed in the basis E prime is equal to the sum from I equals 1 to 3 of the sum from j equals 1 to 3 of Tij prime Ei prime circle cross Ej prime, where Tij prime is not equal to Tij. So what that means is that the representation of the tensor in the basis E prime is not the same as it is in the basis E. So what that means is that if I represent the tensor in this basis E prime, it's not equal to its representation in the basis E. Note, however, that the tensor is the same regardless of the coordinate system. Of the coordinate system, again, same thing as saying basis in this case because we don't really have any origins of the coordinate system basis, right? So that the tensor is the same regardless of the coordinate system used to represent the tensor. Okay, so that's a very important fact that needs to be kept in mind. So tensors are coordinate free. Their representations depend on coordinate systems, just like vectors are coordinate free, but their representations depend on the coordinate system. If I change the coordinate system, I change the representation, but I do not change the quantity itself, whether I'm dealing with a vector or a tensor. And that's very important when we're actually doing algebra, because the actual development of the concepts whenever we use tensors don't have anything to do with coordinate systems, but when we actually start to parameterize and we start to quantify, we need to use coordinate systems in order to represent quantities, and those representations depend upon the choice of the coordinate system. Now, once we've done all this, we actually have a nice sort of structure here that allows us to be able to work with tensors. So whenever we do put things in coordinate systems, we can work with the matrix representations, or we can just work with the tensor products themselves if we want to. But it may be easier sometimes to work with the representations. So what we can do is as follows: is that again? So let's revisit this. So just to make this a little bit clearer, if we take T and we represent it in a basis defined by E1, E2, E3, it looks like the sum from I equals 1 to 3 of the sum from j equals 1 to 3 of Tij Ei circle cross Ej. And then the vector A looks like the sum from I equals 1 to 3 Ai Ei, where this basis E1, E2, E3 is a right-handed orthonormal basis. So then the tensor product, the product of the tensor with the vector is going to equal the sum from I equals 1 to 3 of the sum from j equals 1 to 3. Now, you go through this and you actually get the following result. And let's do this in two steps actually, so we can actually see it maybe a little bit more clearly, which is that we get the following result. We get T11 A1 plus T12 A2 plus T13 A3. This is multiplied by E1 plus T21 A1 plus T22 A2 plus T23 A3, and that's multiplied by E2, plus T31 A1 plus T32 A2 plus T33 A3, and that's multiplied by E3, which we can actually write this way, which is that we can see that the summation actually is taking place about in both the both row wise and column wise because of the way in which we wrote this out. So we can write this as the sum. So we can write from j equals 1 to 3 of T1j Aj, and then this is multiplied by A1, sorry, not A1, E1, plus the second one is the sum from j equals 1 to 3 of T2j Aj, and this is multiplied by E2, and then the last one is the sum from j equals 1 to 3 of T3j Aj, and that's multiplied by E3. So now we have this representation, and maybe just to make this a little bit better, let's give ourselves just a little bit more room here because it may be a little hard to read because it got a little crowded out at the bottom there. So this is equal to the sum from j equals 1 to 3 of T1j Aj multiplied by E1 plus the sum from j equals 1 to 3 of T2j Aj multiplied by E2 plus the sum from j equals 1 to 3 of T3j Aj, and that's multiplied by E3. Now you can actually see that now we can sum over the over these, and this is actually a 1 here, not a T1j. So now we can sum across I if you want to, and we can write this as T operated on A is equal to the sum from I equals 1 to 3 of the sum from j equals 1 to 3 of Tij Aj, and then the whole thing is multiplied by Ei. That's the result. So the inner, if you really want to break it up, you get the inner sum, which is this one, and then you have the outer sum. So that's how this looks. And going back to what we had before, that T operated on A expressed in the basis E was going to equal. So now if we write this out, it's the sum from j equals 1 to 3 T1j Aj. That's what's in the first component. In the second component, we have the sum from j equals 1 to 3 of T2j Aj, and then in the third component we have the sum from j equals 1 to 3 of T3j Aj. And again, let's just make this a little bit bigger. And then just to be so even about this, make t operated on A expressed in the basis E is equal to that, which is also equal to the matrix representation of T in the basis E multiplied by the column vector or the column matrix representation of the vector A in the basis E, which we'll write one more time out so that everybody sees it again. T11 T11, let's make this a little smaller. T12, T13, T21, T22, T23, T31, T32, T33 multiplied by A1, A2, A3. Okay, now we've gone through the details. Now let's do an example to see how this actually works in practice, okay? And this is how tensors are used. Now we're going to do a problem, or we're going to do an example that's actually something that we've studied before, but we're going to study it now in the context of tensors, okay? So recall the vector product between two vectors. And remember the vector product, A cross B. This is a vector product. It's not a tensor product. It's a vector product. All right, the vector product A cross B between the vectors A and B. So if we express the we're going to call something a tensor here. So we're going to say I'm going to call it A cross be an operation defined on the vector B such that, I have to be really careful with the way we write this. It's a superscript. It's A cross operated on B is equal to A cross B. What we're going to do is we're going to show that this operation A cross is a tensor. So in order to do that, we're going to show, so we will show that A cross is a tensor. So how do we do that? Well, let's actually go through the steps. So A cross is the same thing as taking the cross product of A with something, right? So another way of looking at this is that we can say that A cross operated on something is equal to the cross product of A with that same something. All right, it's just an empty argument. I mean, in this case, it's B, but that's how this is. Now, so what we need to show is we need to show that the operation A cross, where we actually take the cross product, is a tensor, right? So how do we do that? We actually do it as follows: is that A cross B, the input is a vector. In this case, that vector is B, and the output is a vector. What's the output? It's A cross B, right? So it satisfies the first condition of a tensor, which is that the input's a vector and the output's a vector. The second thing is if we take A cross with beta B plus gamma times C, what do we get? We get beta times A cross B plus gamma times A cross C, which implies that A cross is linear. So that implies that this quantity, which I defined as A cross, is also linear because it's the same thing as taking the cross product of A with some vector. So that implies that this operation A cross is a tensor. So now actually what we're going to do is we're going to look at what this tensor looks like in a basis, okay? So suppose now that E, which is equal to E1, E2, E3, is a right-handed orthonormal basis for three-dimensional Euclidean space. So then A cross B, well, before we do A cross B, let's just write A. So then A is equal to the sum from I equals 1 to 3 of AI EI, which is equal to A1 E1 plus A2 E2 plus A3 E3. And B is equal to the sum from I equals 1 to 3 of BI EI, which is equal to B1 E1 plus B2 E2 plus B3 E3. So let's go through and take the cross product now. So then A crossed with B is equal to, it's A1 E1 plus A2 E2 plus A3 E3 crossed with B1 E1 plus B2 E2 plus B3 E3, which is equal to. So now let's take the cross product. So we get A1 B2 E3 minus A1 B3 E2, and then we get A2 B1 E3 with a negative sign, and then plus A2 B3 E1, and then we get plus A3 B1 E2 minus minus A3 B2 E1, right? So A3 B2 E1. So this, of course, when we write it all out, gives us, let's look at the E1 components. We get A2 B3 minus A3 B2 times E1 plus we've got the E2 components, which gives us A3 B1 minus A1 B3 times E2, and then plus A1 B2 minus A2 B1 times E3. Now let's go through and do this with tensors. That's the cross product the way we've always done it, right? So let's represent this tensor in the basis, not this tensor, sorry, this cross product. We're going to represent this in the basis E. Well, what does that look like? Well, it looks like these three components, which are A2 B3 minus A3 B2. The second one is A3 B1 minus A1 B3. And then the last one is A1 B2 minus A2 B1. So when we write that out, we can actually rewrite that in terms of the following product of a matrix with a vector. We can write this as something times B1, B2, B3. So what does that look like? It looks like 0 times B1 minus A3 times B2, A2 times B1, B3. And then we get A3 times B1, 0 times B2, and minus A1 times B3. And actually, let's just give ourselves a little bit more space vertically here. We've got A3, 0, minus A1. And then we have minus A2, A1, and then 0. So now if we look at that, we see that there's a matrix, a 3 by 3 matrix multiplied by a column matrix, right? So this means that A crossed with B, when expressed in the basis E, can be written as the product of a 3 by 3 matrix and or with a 3 by 1 column matrix. But remember what we said. We said that earlier that a tensor, when represented in a basis E, there is a matrix that's associated with that tensor. So recall that a tensor T expressed in a basis, which we're calling it E, is a 3 by 3 matrix, because that's the matrix representation of the tensor. So that means that this quantity here, that this is this 3 by 3 matrix, has to be the representation of some tensor, right? Well, what is that tensor? Well, let's look at it. We'll see that, you can see that this, if I actually rewrite this, I can do the following. Is if, suppose we don't, suppose we let A, well, not let, well, let's just say, so suppose we rewrite this. So suppose now that we use this fact, that this last fact is used. So what do we have then? We know that B expressed in this basis defined by E is equal to B1, B2, B3. And also we know that the matrix which is defined by 0, 0, 0, minus A3, A2, minus A1, A3, minus A2, A1, is the representation of a tensor in the basis E. But that matrix arises from the cross product, arises from the vector product from A cross B. So therefore, this matrix, which is defined by minus A3, A2, minus A1, and then with zeros on the diagonal, and then A3, and then minus A2 and A1 on the lower triangular part of it, is equal to, must be equal to, A cross, which is the tensor represented in this basis E. Because then that's the same thing. Remember that this is, I've put this again in quotes, this is equal to A cross, right? And again, that's, represented, if you want to be complete about it, it's represented in the basis E. So as a result, we get the following. A cross, which is my tensor, is equal to, represented in this basis, is equal to this matrix, which is minus A3, A2, minus A1, A3, minus A2, A1. And as a result of that, we get the following. That this tensor A cross, I'm going to put a double underbar here, is equal to, well, if I write it out in terms of the basis tensors now, it's going to equal minus A3 E1 circle cross E2 plus A2 E1 circle cross E3, and then plus A3 E2 circle cross E1, and minus A1 E2 circle cross E3, and then minus A2 E3 circle cross E1, and then plus A1 E3 circle cross E2. That's the tensor. And that tensor is the tensor that's associated with the cross product. So the cross product itself, or the vector product, the first operation, which is that A cross, is itself a tensor. And that tensor actually looks like what I wrote in this last expression here when written out in terms of the basis tensors, EI circle cross EJ. So when written out in terms of the basis tensors, EI circle cross EJ, where I and J go from 1 to 3. So now we have a way of being able to represent the cross product as a tensor. So the equivalent is saying that if you take the cross product between two vectors, the operation of taking the cross product is itself a tensor, and that tensor is associated with this particular matrix. So the nice thing about this now is we can actually take cross products fairly quickly. So what you can do is this: so for a general cross product or general vector product, A cross B, we have that A cross B, when expressed in some basis E, is equal to this matrix, the matrix representation of this tensor in the basis E, multiplied by the vector represented in that basis E, and that's equal to this matrix 0, 0, 0, minus A3, A2, minus A1, A3, minus A2, A1, multiplied by B1, B2, B3. And so that's our example for this lecture. So we've gone through, we've done an example, we've gone through all the theory of tensors, and we've provided the constructs that arise in tensor algebra, both in terms of coordinate-free quantities, which are the tensors and the vectors themselves, and in terms of coordinate-dependent quantities when we express these tensors and vectors in particular coordinate systems, and that leads to the ability to be able to do operations with matrices and vectors, and that's the end of this particular lecture. And in the future, we're going to actually use some of these constructs to be able to do vector operations, and we'll actually define particular types of tensors that will actually be useful in the construct in the context of the kinds of operations that we're going to be using. Now, just to be able to finish this in a complete way, the two tensors that will arise very frequently in future operations are as follows. So we're gonna deal with these tensors a lot. So these are two common tensors, and this is the last thing we're going to describe, and then we'll end this lecture. The first one is what's called the identity tensor. Now, the identity tensor has the following property, which is, and we're going to label this tensor U. U has the property that if I apply it to a vector, I get back that vector. So we can actually write U in terms of a basis, E1, E2, E3, really easily. It's just EI circle cross EI summed from I equals 1 to 3. And you can actually see that that is, in fact, the identity tensor for the following reason. Suppose I take U and I operate on A. What do I get? Well, I get E1 circle cross E1 plus E2 circle cross E2 plus E3 circle cross E3. And that whole thing is going to be applied to A1 E1 plus A2 E2 plus A3 E3. And that's equal to, well, if we take these products, we get A1 E1, E1 circle cross E1 applied to E1 is E1, plus A2, and then E2 circle cross E2 applied to E2 is equal to A2, so A2 E2 plus A3 E3, which is equal to A. So that tells me that U dotted with A is equal to A. So that is the construct for the identity tensor. The last one, which will be the thing that we will use also in the future quite commonly, is what's called the transpose of a tensor. So if T is a tensor, then T can be written in terms of basis tensors, or I should say T can be represented as T is equal to the sum from I equals 1 to 3 of the sum from j equals 1 to 3 of Tij Ei circle cross Ej. Then the transpose of T, which is denoted T transpose, is represented as T transpose is equal to the sum from I equals 1 to 3 of the sum from j equals 1 to 3 of Tji Ei circle cross Ej, which also happens to equal the sum from I equals 1 to 3 of the sum from j equals 1 to 3 of Tij Ej circle cross Ei. So I can either change the order of the basis tensors or I can change the order of the elements. Now from that we can actually write this out. So then if we write out T in terms of this basis E, which I've been using throughout this discussion, we get the matrix that we wrote down earlier, T11, T12, T13, T21, T22, T23, and T31, T32, T33, which implies that T transpose expressed in this basis E1, E2, E3 is equal to T11, T12, T13, T21, T22, T23, T31, T32, T33. And that is the transpose. That this also happens to equal, when we get to matrix algebra, this is also equal to T expressed in the basis E and then the transpose of that. They're the same thing. So that is we'll be using those two tensors during other discussions, so they're useful to know about now. So that's gonna end it for this particular lecture, and then in the next lectures we'll actually go forward with more operations on tensors when we actually need them in the study of dynamics. In particular, we're going to need this in the study of rigid body mechanics.